Hi everyone, we're the Classifying Vaccine Misinformation in Text group. I'm Aakash Kothapally, and I'm presenting alongside Dave Sate. And this summer, we've been mentored by Ricard Sturborg, alongside Professor Luan Dingra, as well as Professor Jun Yang of Duke. So let's talk about vaccine misinformation. So misinformation is widespread. For instance, this idea that the CDC is hiding negative effects of COVID vaccines is believed by about half of Americans. And among those who believe in this piece of misinformation, a significant portion of them are unwilling to take the COVID vaccine, whereas among those who do not believe in this piece of misinformation, nearly all of them are willing to take the COVID vaccine. And the effects of this are severe because, as the White House COVID task force revealed recently, nearly all current COVID-19 hospitalizations in the United States are occurring with unvaccinated people. So our inability to vaccinate people, which can be drawn back to the belief in misinformation, is causing hospitalizations and issues in the United States.
So what's the specific problem that we're trying to solve? The problem we're trying to solve is, let's say, given a text like this from the internet. So this is clearly an anti-vax text. It's talking about how the polio vaccine can increase the risk of brain tumors and cancer. And it's also claiming that taking the flu vaccine makes you more likely to get hospitalized with the flu. Given some text like this off the internet, we asked two questions. The first one is it vaccine misinformation, which is just a yes or a no? And if yes, then the second question is, what's the specific misinformation argument being made by this text? In this case, it's attacking vaccine safety and claiming that there are health risks to taking the vaccine. And we want to be able to classify these misinformation arguments into a taxonomy that's been made by in previous work by our research team, which essentially classifies all the different types of common myths and groups them into different categories. So you can see here, the example that I just showed you belongs to category 3, which is health risks and attack on safety, because it's talking about how you can get the flu vaccine from taking the flu vaccine. So it falls into contracting the disease from the vaccine, as well as the side effects about brain tumors from the polio vaccine fall into category 3.3 and 3.3.2 specifically. So this is a hierarchical taxonomy, which is to say it's organized into different levels of detail for different categories, as well as it's important to note that one piece of text can correspond to multiple parts of this taxonomy, which makes this a hierarchical multi-label classification problem. So our approach to solving this problem is creating an NLP pipeline, and this is the majority of the work that we did this summer. So this pipeline is automated, and it goes all the way from receiving collected data to cleaning that data, training models based on that data, evaluating those models, and then running further experiments that answer questions about all of these parts of the pipeline. The first step of the pipeline is data collection. So this data collection happens on an existing corpus of misinformation articles that's been compiled by our research group in previous work. And we conduct annotations on this misinformation article through mTurk. So this is what the UI looks like for mTurk. This is a crowdsourcing platform run by Amazon. And we have hundreds of annotators on this platform. And this is a view of what they see. So they see articles split into different paragraphs. And for each paragraph, they have to answer whether that paragraph belongs to a specific part of the vaccine misinformation taxonomy or not. And they just answered yes or no questions. And each annotator is assigned one of the 5 main branches of the taxonomy. So each major branch is a different color in this diagram on the left. And each annotator only makes annotations for one of these 5 branches. And they make annotations, so they say a yes or no for the high level label of that branch. And then for the subcategories, they pick which of the subcategories apply. And as you can see, they can pick multiple subcategories at once as well. And based on this scheme, we've collected 250,000 annotations across 55,000 different paragraphs. So the next step after collecting this data is to clean it, which Aakash will talk about.
Yep, and so to do data cleaning, one of the main tools we use is Pandas to do that cleaning. And after we're done cleaning, we convert to a Hugging Face dataset. So Hugging Face is an NLP library that specifically aids us with our model training. And so this is sort of the result of what we have. We keep track of certain identifiers, stuff like paragraph, article, ID, and we also keep track of obviously the content of each paragraph. The important point here is that we only keep paragraphs for which all of these taxonomy labels have been annotated by an M trigger. And as Dave mentioned, we do multi-hot encoding for each of these taxonomy labels, meaning that any paragraph can be assigned 0, 1, or multiple of the 5 top-level labels, as well as the labels that are within those 5 top-level labels that are within those branches.
So after data cleaning, we take the data that we just cleaned and put it in a nice format, and then we send that data to models for training. So we use a variety of tooling for this. On the hardware side, we use the resources from Duke Research Computing. They have a GPU cluster that we use. And then on the software side, we use mainly an NLP library called Hugging Face, which makes a lot of NLP tasks much easier for us. And underneath all of our software is PyTorch, which is a tensor manipulation library for doing computations on a GPU. And then for logging all of our metrics and comparing experiments and creating visualizations, we use the online machine learning dashboard, weights and biases. Using all of these tools, so far we've trained 4 different model architectures, going from Distilbert. So all of these architectures are created by large companies. These are very large scale pre-trained models, and we're fine-tuning them for our specific task of classifying vaccine misinformation. And so we went from Distilbert, which is a model by Google, all the way to GPT-2 Large, a model by OpenAI. And there's an order of magnitude difference in the number of parameters of these models. So we've scaled our pipeline to be able to train, going all the way from smaller models to very large models.
So next we'll do model evaluation, and some contemporary metrics that we use are stuff like accuracy, precision, recall, specificity, and F1 score. In addition, we have a supplementary metric, the ROC curve. So to explain what the ROC curve does, it's essentially explaining how much better your model is than random at distinguishing between positive and negative classes. So for the purposes of our research, a random classifier would falsely classify a piece of misinformation or correctly classify a piece of misinformation at roughly equal rates, whereas a perfect classifier would not make any mistakes. So namely, it would never classify a piece of misinformation as non-misinformation, and it would never classify a piece of non-misinformation as misinformation. Essentially, we want to see where between that red line and that purple line our model falls. The closer to the purple line, the better. And a way of encapsulating that sort of result is something called the area under curve, AUC of the ROC, where you just take the area under the curve. And obviously a higher area means you're closer to purple, which means better.
So after doing all of the steps of the pipeline, we run experiments to answer different questions we have about the model training process and performance and how different factors affect that. We've conducted experiments in 3 different categories. The first one is, how do hyperparameters affect performance? Hyperparameters are parameters to the training pipeline itself. So things like what's the learning rate, what's the batch size, etc. The second class of experiments is about asking questions about data quality and how that affects performance. And the third one is talking about robustness, or how well does our model respond to things that it has never seen before. So let's talk about the first one, which is, how do hyperparameters affect prediction performance? Our goal with this experiment was to find ideal hyperparameters for all of the different model architectures using a technique called grid search. Grid search is essentially brute forcing. So we find all the different combinations of hyperparameters for all the different values that we want to test. And then for each of those combinations, we just train the model based on those hyperparameters. And then at the end of doing hundreds of different training runs for different combinations, we compare the performance metrics and see what combination of hyperparameters is suitable for our model. And so based on that, we find So this is just a table of some important hyperparameters that we found based on this process, as well as how they, whether they correlate positively or negatively, weakly or strongly to the model performance. So overall, we found that hyperparameters related to our optimizer, such as Adam, beta 1 and weight decay, these are both related to our optimizer Adam. These are end up having a lot of influence on the model performance. And we also find that a smaller batch size during training helps the model to learn better, as well as applying gradient accumulation helps larger models specifically to learn better, where gradient accumulation is the process of adding up gradients across multiple steps before computing an update step.
So next, we'll talk about how data quality affects prediction performance. So the important thing here is that we're relying on M-checkers, so humans are involved. And because of that, there's unreliability in the data set. So what we do is occasionally we evaluate these annotators for accuracy with quality checks. And for annotators who fail these quality checks, we ban them from making any further annotations, and we deem their past annotations as unreliable. However, the issue with this approach is that under this purview, around half of the annotations we have are unreliable. And as you can see in this chart that shows for each taxonomy label the occurrence of banned annotations, this is a problem that extends throughout all taxonomy labels. It's not unique to just one. Throughout, around half of the annotations we have to work with are unreliable. And because of this, around 4/5 of the paragraphs that we have, because each paragraph has these 5 taxonomy labels, around 4/5 of the paragraphs that we have at least one unreliable annotation. So that means 80% of our paragraphs are working with unreliable annotations at some scale. And so to look at this, we wanted to do sort of an experiment to see whether this unreliability was an issue. So our experiment was we first trained on a set that only had reliable paragraphs that only had reliable annotations. And we compare it to the overall data set that doesn't care about whether or not annotations are reliable. And the results here, these are the ROC curves on our simplest model to Hilbert. So the blue line represents paragraphs that only have reliable annotations. And there's only 1,740 paragraphs to work with. Whereas the yellow line represents a model trained on all of the possible paragraphs we have, which is 10,440 paragraphs. So it's 6 times as many paragraphs to work with. Yeah, as you can see here, the blue line is a lot more closer to perfect. The yellow line is a lot more closer to random. And specifically the AOC measurements, the reliable set, which is 6 times smaller, is higher than the one for a larger set. And so from this, we can observe that the model that's only using this reliable data is outperforming a model that has 6 times as much data to work with, and which about half of which is unreliable. So from this, we can conclude that on some level, training is sensitive to noise, and we figured that we needed to do further investigation to determine whether this would hold for a smaller amount of noise. So we can see that this holds for a binary comparison of reliable versus overall. And now we can see with a more finer grained comparison how that is. So Dave, you can take it away.
So let's look at this experiment. What we did here was we trained on data that's fully reliable versus data that's partially reliable, but like is mostly reliable. So so the 2 different experiments are we have paragraphs that, so the green model is trained on paragraphs which are completely reliable, which is to say that all 5 of the annotations for that paragraph are reliable. The red model is trained on paragraphs which are either completely reliable or have at most one of the 5 annotations being unreliable. So the training set for the red model includes the training set for the green model and some more paragraphs. So we find that the green model, the model trained on the green set, which has 3 times less data than the model trained on the red set, with like 13% less noise, ends up outperforming the model which has a lot more data with just a little more noise, right? So what we're basically seeing here is that adding 13% more noise to this data is completely negating the impact of having 3 times as much data, which means that our models are very sensitive to noise in the training data set. But a secondary conclusion for this is that the banning process that we're using is very meaningful, which is to say that the process that we use to determine which annotation is reliable and which annotation is unreliable is actually working, because it's effectively filtering out annotations that our models can learn better from annotations that our models are not able to learn as well from. So we know at least one of the more upstream parts of our pipeline is working properly. Now, this leads us, so let's evaluate where we are right now. We observed from one experiment that about 80% of our data set relies on at least one unreliable annotation. So 80% of all the paragraphs that we have in our data set, all of these paragraphs have 5 annotations, and 80% of them have at least one unreliable annotation among those 5 annotations, right? So which is to say, like, a majority of our data set relies on unreliable annotations. But we also found that if we train on data that contains even a small amount of unreliable annotations, then that harms our performance. So if we chose to do nothing about this, what this would mean is that we just need to throw out about 80% of our data simply because it contains like 20% or more unreliability within the data. And we would only be able to train with a very small amount of our data. So we wanted to find a means to salvage this like vast majority of our data, which, you know, is like has mixed reliability. And what mixed reliability means here is that a paragraph is considered to have mixed reliability if some of its 5 annotations are reliable and some of its 5 annotations are not reliable, right? And most of our paragraphs have mixed reliability. So we did this experiment where we applied a technique called label masking, where for each paragraph, only the reliable annotations of that paragraph are considered during training. So the unreliable annotations for that one paragraph are essentially hidden away from the model when it's training. So which has the effect of the model never learning from the unreliable annotations. And what should happen after applying this technique is that we should have a much larger data set, which contains both unreliable and reliable annotations. But when we train on that data set, our model only looks at the reliable annotations within that data set, allowing us to salvage most of our data. And so we trained another model on this large data set which has like paragraphs of mixed reliability. And we find that it gets outperformed by this earlier model, which is trained on completely reliable paragraphs, right? And this is very surprising because we would expect model B in this case, which is trained on 10 times more data using label masking, to perform at least as good as model A, which is trained on fully reliable data, since the only difference between model A and model B is the amount of data and not the quality of data effectively after applying this label masking technique. So this was a very counterintuitive result. And we're still doing further analysis on this to be able to explore exactly why this is happening.
So next we'll talk about how robust our model is. So one experiment we did on this was we inserted news articles from places like the Washington Post, NPR, and The Guardian. They're just completely unrelated to vaccine misinformation. And we made sure they made up a majority of our training set as well as half of our test set. And we wanted to see how that would impact what the model's results were. And so with specificity specifically, we see a big jump. So specificity is describing, for our research, the proportion of cases where there is not misinformation, and we're correctly saying there is not misinformation. So our original model tends to do very poorly at that, but this new model that introduces this new training data sees a big improvement in specificity. And as a result of this improvement in specificity, there's also an improvement in the ROC curve and the ensuing area under curve calculation. So you can see the blue bars represent sort of our initial or our original model, and the green bars represent us introducing these news articles. And you can see that distinguishing between positive and negative classes becomes a lot better once we have inserted these news articles. So we observe obviously that specificity is improving a lot, and that's what's improving the ROC and the AUC score. And from this, we can conclude that our model is able to perform well at separating between just pure vaccine misinformation as well as just unrelated news that has nothing to do with vaccine misinformation. So it's a positive result that we'll take going forward.
And as we're nearing the end of our presentation, we wanted you to see directly like how the model performs on some very specific examples. So for example, this is a New York Times article about the Olympics, which has nothing to do with vaccines. And the model predicts a very low score for all the categories, meaning it doesn't think that any of the vaccine misinformation categories apply to this, which is correct. And then here is another post from the Moms Against Vaccines Facebook group, which has a wealth of vaccine misinformation. Specifically, it's talking about, it's questioning like why doctors don't do a specific thing. It's also questioning the ingredients of vaccines. And let's see what the model predicts. So the model is able, like with a high level of confidence, predicts that it's attacking the safety of vaccines, specifically the harmful ingredient subcategory. And it also thinks that there's a criticism of authorities happening here, which we can see is like questioning the information being given by the doctor. So we see that the model is able to learn to some extent, at least, how to differentiate between non-misinformation and misinformation, and also how to distinguish between the different types of misinformation within an article. With that, we end our presentation. Thank you very much. And remember to get vaccinated.